Welcome to Brain Vision.
That's problem. We have a Rankine cycle again, and we have operating between pressures of 1500 psi and 2 psia. And let's see here. We're told the temperature here is 800 degrees C, or 800 degrees Fahrenheit. The turbine efficiency is 90%. We're assuming that there's no losses in the pump, so it has an efficiency of 100%. We're given the net power output as 2,500 kilowatts. Okay, so this is an English units problem, so we'll be needing to use this conversion factor between BTU and kilojoules. In fact, one kilojoule is very close to 1 BTU. So, but we need to convert because this is kilojoules per second, and we need it to be BTU per second. So we'll need to do some conversions along the way here, whatever we need to. So let's see, let's get on with it then. Saturated liquid here, so we know the pressure, so we get the enthalpy and the specific volume. We can figure out the work from the pump is just, again, we're assuming incompressible liquid, so specific volume doesn't change, but the pressure goes from 2 psia to 1500 psia, which means we have a specific work in the pump of 4.5 BTU per pound mass. Conservation of energy then tells us that the enthalpy at point 2 is enthalpy at 1 plus the work that went into the pump, specific work went into the pump, so we got 98.52 BTU per pound mass. We have two thermodynamic properties here at 3, so we can get the enthalpy and the entropy there. We only have one thermodynamic property at 4, but at point 4 prime, we know that the entropy S4 prime is S3, so that gives us two properties to find out at this point for the isentropic case. And that gives us a quality factor of about 76.3% and an enthalpy of 873.86 BTU per pound mass. We know the efficiency, and we know the relationship between the enthalpies and the efficiency, the thermal efficiency, the isentropic efficiency. So we can figure out what the actual enthalpy at point 2 is, and that winds up being 922.79 BTU per pound mass. So I'm not sure, I didn't calculate what the entropy was here. I know it's going to be greater than this, but I'm not sure if it's in the phase region here or not, whether it's inside of the the dome here or it's outside. I'm not sure. I didn't calculate that, and we didn't need it. So you could do that obviously, because now you have pressure and enthalpy. You could then figure out what the temperature is too. Well, that would be an interest if the temperature, it might be saturated. Yeah, it may have to be at the saturation temperature. It may be a little higher. But that would give you, using this and this, you kind of guess on what the temperature was and then, iterate. Anyway, the heat transfer in is enthalpy here minus the enthalpy here, and that winds up being 1,265 BTU per pound mass. Enthalpy, heat transfer, specific heat transfer out is the enthalpy here minus the enthalpy here. That winds up being 828.8 BTU per pound mass. The net work is just the difference of these, and that winds up being 435.8 BTU per pound mass. Now, to figure out the flow rate, we can just use the formula here that the power output is the mass flow rate, the mass flow rate through this system times the specific work. The only thing here to be careful about is we need to convert this to BTU per second using this conversion factor. Converting that and then dividing it by W net gives us M dot as 5.437 pound mass per second. Now, and this should be kilowatts because I converted that too. So then we are asked about the let's see here, from the turbine. and the rate of heat addition. The power output from the turbine and the rate of heat addition. Okay, so the power out from the turbine is then just m dot, which we have, and then times the difference in enthalpy from 3 minus the enthalpy at 4. So here, from basically the enthalpy change along this curve, along this process here. And then I converted it to kilowatts. So that winds up being 2,526 kilowatts. Again, that should, you notice that's higher than this, but we should find that if we look at the rate of power into the pump, then, that should be consistent then. The rate of heat transfer in, again, we know the mass flow rate, and we know the specific heat in. And so that winds up being 6,876 BTU per second. So, that's very close to being kilowatts because of this conversion factor is pretty close to 1-to-1. Anyway, we can then figure out what the thermal efficiency of the cycle is, and that would be the net work out, wherever it is here. And again, me converting that to BTU per second or converting this to kilowatts, either way, we need these two things to have consistent units because the units need to cancel out. And in that case, we get 34.5% is the thermal efficiency of this cycle.